just like how the addition rule is used to compute the probability of A or B, the multiplication rule is used to compute the probability of A and B occurring at the same time. So I'll just say joined by and. So i.e. probability of A and B, it is the same as writing it as A intersect B. And now, of course, we can extend it to more than one event. I'll simply write that also. So what does the rule state? So probability of A and B is equal to the probability of A multiplied by the probability of B. If A and B are independent of each other. What does independence mean? So two events are said to be independent if the occurrence of one event does not have an effect on the occurrence of the other. So the rule that I wrote, that probability of A and B is equal to simply the probability of A multiplied by the probability of B, can only be used if A and B are independent of each other. So what does independence mean? Well, if A happens, it doesn't have an effect on B. And B can have the same probability, whatnot. So in terms of an example, let's say I roll a 6-sided die twice. And I'm going to call A to be outcome of the first roll, and B to be the outcome of the second roll. We want to know if A and B are independent. Now I'll just specify the outcome when I write this probability. So So is A equal to 2 and B equal to 2 independent of each other? So if I get a 2 in the first rule, does it imply that you cannot get a 2 in the second rule? No. Would the outcome of the first rule have any effect on the outcome of the second rule? Absolutely not. So the second time you roll the die does its own thing. It doesn't have any effect introduced from the previous rule. So A and B are independent events. So that would simply mean probability of A equals 2 and B equals 2 simply would mean that we get rolling a 2 in both times or simply say both times. So you get a 2 the first time, you get a 2 the second time, and clearly the second time you roll the die, it's not affected by the first time you roll the die, so the events are independent. So I could simply say probability of A equals 2 multiplied by the probability of B equals 2. But we know what the probability of getting a 2 when we roll a 6-sided die, so it is simply 1/6. It is the same for the second case, probability of B equals 2, which is also 1/6. So 1/6 times 1/6 would simply be 1/36. How would we go about extending this to more than one event? Suppose A1, A2, A3, ... all the way up to AN are independent events. In other words, the occurrence of one event doesn't affect any of the others, and vice versa. They don't have any connection whatsoever. Then the probability of A1 and A2 and A3 all the way up to AN is simply the product of each of their probabilities. So probability of A1 times the probability of A2 times the probability of A3 all the way up to the probability of AN. In other words, we simply find the probabilities of each event and multiply them all together. Hence the name multiplication rule. And when we do multiplication rule, it is always important to recognize when to use the following rule, which is derived from the complementary rule. So the at least one and none rule. So the probability of at least one of something, it could be anything, at least one, 6 in 17 die rolls, at least one tails in 512 coin tosses, and so forth, is simply equal to 1 minus the probability of none. So as an example, I'll write it out. So probability of at least one tails in 824 coin tosses is simply equal to 1 minus the probability of no tails in 824 coin tosses. So finding at least one probability without using this rule will take forever. So if you fall into the trap and if you don't recognize it as an at least one and none problem, you're going to waste a lot of time trying to find the probability because you're going to get stuck. So anytime you have an at least one probability type question, always ask yourself, could we do this problem with the complementary rule or the at least one to none rule? We've done problem like this in the previous video, but this particular rule is quite often used with multiplication rule and independent events.
Professor, I know this is not a question.
So the ELISA is a test to determine whether the HIV antibody is present. ELISA stands for enzyme-linked immunosorbent assay. They say that the test is 99.5% effective, which means that the test will come back negative if the HIV antibody is not present 99% of the time. So the probability of the test coming back positive when the antibody is not present, in other words, a false positive in the sense the test is telling you that you've got HIV, and in reality, you don't have HIV. That is only about 5 in 1,000, so 0.005. Suppose that the ELISA is given to 5 randomly selected people who do not have the HIV antibody. In other words, they don't have a HIV infection. What is the probability that the ELISA comes back negative for all 5 people? Now, note, or we're going to assume don't have to assume, but note the 5 people are randomly selected in the sense they are not related in any shape, way, or form. We all know that if you are in a relationship with someone, and if they turn out to be positive, then you are going to be positive also. But that is not the case here because we are selecting random people. So that would simply mean that the 5 people are independent of each other. So let's say I will call the ith person test as AI. So A1 through A5. So we want to find the probability that the test comes back negative for all 5 people. In other words, we're going to find the probability that there are no false positives. So the first person is negative, and the second person tests negative, and the third person tests negative, and the fourth tests negative, and the fifth tests negative. All 5 of them test negative. Since they are independent, we simply multiply the probabilities. What is the probability that they're all independent? Probability that we'll get a true result, in other words, no false positive. it is 0.995. So 0.995 for the first person, 0.995 for the second, 0.995 for the third, fourth, and fifth. We simply have to multiply them, and that probability should be 0.94 something. We'll see, 0.97. So what is the probability? All 5 of them come back negative, 97.52%. So what is the probability that the ELISA comes back positive for at least one of the 5 people? So this is where the at least 1 to none rule comes into play. So the question wants to know the probability of at least 1 coming back positive. In this problem, that simply means that at least 1 false positive, because none of the 5 people are positive for HIV. And we're asking the question, what are the chances at least 1 end up being positive? So whatever positive result is going to happen must be a false positive. At least 1 false positive would simply mean 1 minus the probability of no false positives. That simply would mean all 5 of them are true negatives. No false positives imply every single one of them were tested and they all happen to be true negatives. What is the probability of finding a true negative person? It's 0.995, so 0.995 raised 5. We know that answer from the previous part, 9752. So that would be 0.0248. So if we have 5 people, what are the chances that at least one of them would end up having a false positive? It's about 2.5% chance. That is why, if I recall correctly, even though the ELISA test was used long time ago, it resulted in a lot of false positives, but we had a lot of people, which is why we now have these 4th generation HIV tests, which are much more effective and doesn't have a very high probability of false positives.